So in our previous lecture, we learned about the harmonic oscillator, how it looks like, and how to describe the motion of diatomic molecules. So we can separate the motion of diatomic molecules into two separate motions, right? The translational motion, which means the center of mass moves around in the space. And we also have the vibrational motion, which reflects the change in the relative coordinates of two atoms, right? And we also discussed the validity of the harmonic oscillator approximation. So this is the result of applying Taylor's expansion on the potential energy surface of diatomic molecules. So we can take the potential energy of the minimum as the zero because the absolute energy does not really have impact when we interpret the chemical reactions. Also, we can say that the first derivative of the potential energy surface near the minimum is zero, right? Because the minimum of the potential energy surface is characterized by the nearly vanishing slope at that point. So that's why we have the second order polynomial is the leading term when we expand the potential energy surface. And today we are going to discuss more about the quantum things in harmonic oscillator. So the energy levels of quantum mechanical harmonic oscillator are so section 5.5, the energy levels of quantum harmonic oscillator. So we are now discussing the harmonic oscillator in quantum mechanics region. And their energy level is quantized, so as you can see here. And there are two very confusing notation here. So the first one here is nu, Greek letter nu. So this represents the frequency. And there is a B here. This represents the vibration energy level. Vibration energy level. So they are totally different things, but they look very similar. So please be careful when you write the expression for the harmonic oscillator energies. So one-dimensional Schrödinger equation for harmonic oscillator with reduced mass should be h bar square over 2 mu should be given like this. So we replace the potential energy part Vx with the potential energy of the harmonic oscillator, half of the k multiplied by x squared. So you might think that this is more complex equation to solve than the one-dimensional particle in a box problem because there is no potential in one-dimensional particle in a box. So we can solve that quite easily, but as you can see here, so this is not really easy equation to solve, but somehow we can solve this equation analytically, which means we don't need any approximation to solve this differential equation. So for now we are not going to solve that, but I think we will revisit this equation later in this lecture. So let's jump into the final conclusion. So the energy levels that can be obtained from this one-dimensional harmonic oscillator Schrödinger equation, this should be h nu, hb. Energy is given as the h nu multiplied by b plus half. So actually this is quite this equation implies many important consequences. So as you can see here, if you write down the allowed energy levels, the lowest energy level should be half of the HANU. Something like this. So what about the energy difference between the adjacent energy levels? So energy separation is HANU, HANU, HANU. So all the energy levels between the adjacent energy levels should be equal as the HANU. And another noticeable thing is the lowest energy is not zero. So if you think of the classical harmonic oscillator, the classical harmonic oscillator can have the zero energy, right? If you have the harmonic oscillator at rest at the equilibrium length, then that harmonic oscillator should have the zero energy because it is not moving and it is at the equilibrium position, so it doesn't have kinetic energy nor the potential energy. So classical harmonic oscillator, the lowest energy should be zero. This equation looks quite weird, so the lowest energy should be zero. But for quantum harmonic oscillator, what about the lowest energy should be half of the HANU. So this minimum energy is called 0 point energy. Can anyone make a comment on this? Why does the quantum mechanical harmonic oscillator can never have the zero energy? So if you try to remember the Heisenberg uncertainty principle, so this principle states that it is not possible to measure the position and the momentum at the limited, we cannot really accurately measure two these quantities simultaneously. So mathematically this is expressed like this. And let's think about the total energy of the oscillator. Total energy of the oscillator should be given as the sum of the kinetic energy and the potential energy. So the kinetic energy should be the square of the momentum divided by the mass, and the potential energy given as the half of the kx square. So if we want to say that the total energy was zero, if you want to say this is like zero, so this is actually not possible, but we assume that. So if the total energy was 0, then that means the momentum should be 0 and the position should be 0. So the value, the position value 0 and the momentum value 0 has the special meaning. So if you want to say that the position equal to 0 and the momentum equal to 0, that means there should be no error or deviation when you're measuring these properties. Right? If there is any single particle that has the energy different from 0, that sorry. So if there is any particle that has the energy different from 0, then you never have the energy 0. So that means all the particles' energy and all the particles' momentum, all the particles' position should be 0. So that's why we can say that. So, but we we know that the Heisenberg uncertainty principle is like a fundamental principle. This is not a limitation of our measurement. So we know that this is not possible. So that means both the position and the momentum could not be 0 simultaneously. So that's why we have the 0-point energy for quantum mechanical harmonic oscillator. Because the harmonic oscillator's total energy is the sum of the kinetic energy and the potential energy, and this is the region. Okay? Okay, let's move on to the next section. Next section. So section 5.6, the title is The Harmonic Oscillator Accounts for the Infrared Spectrum of Diatomic Molecule. So we already know that the harmonic oscillator is a very fundamental Bayesian model to describe the diatomic molecules, but why do we particularly mention the infrared spectrum? So this is about the energy region. So we can calculate the energy of the diatomic molecule, like typical diatomic molecule, and to see if that is corresponding to infrared region. So I guess you are very familiar with the infrared spectrum. So I guess you have a chance to measure the infrared spectrum in organic chemistry experimental lecture, right? So in the organic chemistry lecture, there are the section that discuss the infrared spectrum of some functional group, like carbonic group has the I cannot remember exactly, but the carbonic group has the characteristic peak at near the 1800, right? Okay. Anyway, the functional group has their own characteristic peak at the infrared region due to the vibration motion. So yeah, we are going to check that. So as we discussed in the previous section, the vibrational energy level of harmonic oscillator is given as this. So actually all the spectroscopy is associated with the absorption and the emission of that energy. So we are measuring the absorption or the emission from each transition. So that means we need to examine the absorption energy and the emission energy based on these quantized energy levels. So you know that according to Bohr's resonance condition, Bohr's resonance condition. The molecule can jump from a lower energy level to higher energy, like V equal 0 to B equal 1. When you shine or when you irradiate the photon that has exactly the same amount of energy as this energy difference. So the Bohr's resonance condition means that the energy difference between two states should be equal to the energy of the photon. So photon's energy is given as the Planck constant multiplied by the observed frequency. So even though we haven't discussed the vibrational selection rule, so let's assume that in a quantum mechanical harmonic oscillator, the selection rule for the vibrational transition is delta V equal to plus minus 1. So let's assume that for now. I think we can discuss the vibrational selection rule when we after we understand the structure of harmonic oscillator's wave function. So let's discuss that later. And anyway, so the vibrational selection rule is delta B equal to plus minus 1. That means the molecule can jump from the from one vibrational state to the other vibrational state, where in only the case where the difference between them is 1. So you can think of that the transition from B equal 0 to B equal 1, it is possible because the difference of the vibrational quantum number is only 1 here. So you can see this, and actually this corresponds to the absorption. So we also discussed that later, but this is the exact transition when what you observed in IR spectrum. So you might think that so B equal 1 to B equal 2 is also vibrationally allowed selection. This is also possible, but this is not a mainly responsible for the vibrational spectrum, because nearly all the molecules are staying at the vibrationally ground state here. So even though this is the allowed transition, but we don't really have a chance to observe this transition. So what about this transition? B equals 0 to B equal 2. So according to the vibrational selection rule of the harmonic oscillator, so this shouldn't be allowed, forbidden. But also we are going to discuss that later. This is somehow very weakly allowed. So this is forbidden in harmonic oscillator. But if you include the anharmonic effect, then this becomes slightly allowed transition. So weakly allowed with anharmonicity. Okay. And let's discuss then this energy difference, delta E. So we know that the vibrational selection rule is delta B equal to plus minus 1. So that means the transition between the adjacent energy levels is only allowed. So in general, the energy difference for the allowed transition should be written like this. And that means so if you do the math, then you will obtain that the energy difference should be equal to Ha nu. So the second equation for the energy difference is from the allowed energy levels of harmonic oscillator. And the first expression is from the Bohr's resonance condition. So we can say that, they are the same expressions, so delta E should be equal to the photon's energy, and this should be the Ha nu. So that means the photons with the frequency, which is the exactly same as the molecule's vibrational frequency, can vibrationally excite the molecule. Okay, and there are many technical issues, like in some technical issue, some spectroscopists want to report the frequency in the units of wave number rather than the frequencies in the per sec unit. So to do this, they introduced omega tilde, which is simply the frequency divided by the velocity of light. So let's take a look at the example of the hydrogen chloride. So observe the fundamental absorption for the hydrogen chloride is about omega tilde of 2886 wave number. And you can calculate from theory, and you might find that the theory is actually well reproducing this value. So there is a connection between the very fundamental theory and experimental observations. Okay, let's move on to the next section. Okay, section 5.7 is about the overtones. So overtones are observed in vibrational spectra. So harmonic oscillator is the very first approximation from the Taylor expansion of the true potential energy curve around the equilibrium bond lengths. So we can say that if you have the potential energy surface, Vx, then we can apply the Taylor series expansion. So the absolute energy, we just take the absolute energy as 0, and the first derivative is vanished, and the leading term is the second order polynomial. So the first term is the leading term, and this is the basis of harmonic oscillator approximation. And the terms beyond the first one, the third order and fourth order, are the anharmonic term. Anharmonic. Even though they are very small, but they still are responsible for the deviation from the ideal harmonic oscillator. So when these anharmonic terms are included in the Schrödinger equation, so we are not trying to solve the Schrödinger equation with these anharmonic terms. We get but with the inclusion of this anharmonic term, we get a more accurate energy for the vibration energy levels. So it should be given energy level is the so for here the omega E tilde, this is the harmonic frequency. So you will easily realize that the first term is from the harmonic oscillator approximation, and the second term, this is from the anharmonicities. So we haven't discussed the structure of wave function of the harmonic oscillator, but once you study that, actually the cubic term doesn't really contribute to the energies, and you will realize that the fourth order polynomial is the first leading term that makes the difference from the ideal harmonic behavior. And so this x E tilde, this is the anharmonic constant. So even though we haven't solved this equation by ourselves, but we can still interpret the final result of the anharmonic oscillators. So comparing with the ideal harmonic oscillator with equally spaced energy levels, the anharmonic oscillator represents the energy level with decreasing gaps. Right, so this is the harmonic oscillator's energy gap. So you know that the gap between the adjacent energy level should be h nu. But what about the anharmonic oscillator? So as you can see here, the second term in the energy expression, this one. So as you can see here, this anharmonic contribution is quadratically increases with the vibrational energy levels, right? So that means at the ground state, their impact is small, getting larger, getting larger, getting larger. Because the anharmonicity increases with the square of the vibrational quantum number. So that means the energy gaps between the adjacent energy levels keep decreasing. So this is one of the results of deviation from ideal harmonicity. So no longer equally spaced energy levels. And there is a second impact of including this anharmonicity. The second, the appearance of overtones. Yep. So unfortunately, we have a very low battery. So we still have 10%. So let's hope that my iPad doesn't die before our lecture time. So in the harmonic oscillator, the selection rule is given as the delta B equal to plus minus 1. But when you include the anharmonicity, this selection rule is a little bit relaxed. And that means with this anharmonicity, we are starting to observe the transition for delta B equal to plus minus 2, plus minus 3, something like this. So without knowing the structure of the wave function, so we can just assume that, okay, this is true. But in this, maybe the next page, we are starting to derive the wave function of the harmonic oscillator. So let's just be more patient and let's just accept this result. So as I mentioned, this is from the ideal harmonic oscillator. So we call this band is fundamental. And this is the strongest band, which means this is the strongly allowed transition. And as I mentioned, for the absorption, the transition from B equal 0 to B equal 1 takes the largest portion of this band. And the overtone, this is the weak band at roughly twice the fundamental frequency, because this is the transition from B equal 0 to B equal 2. So this is the first overtone. Then what about the second overtone? So that should be B transition from B equals 0 to B equals 3. And the frequency corresponding to the first overtone should be first overtone. So there is no, this is not quite common expression, but let's just say that. The frequency of the first overtone is nearly the double of the fundamental frequency. So I wouldn't say this is exactly twice of the fundamental frequency, because with the inclusion of the anharmonicity, the energy gaps becomes smaller and smaller compared to the ideal harmonic oscillator. So if you observe the overtones in the vibrational spectrum or IR spectrum, this is the evidence of the anharmonicity in your molecules. So if your molecule doesn't really have the anharmonicity impact, then you would observe only the fundamental transition, but otherwise there will be small and weakly allowed transition corresponding to these overtones. Okay. And let's discuss the population of vibrational states. So you might wonder why all these transitions, fundamental or overtones, originate from the V equals 0 ground state. So as I already mentioned, so nearly all the vibrational transition starts from the ground state, which means V equals 0. So we are trying to figure out the region. So the answer lies in statistical thermodynamics, specifically the Boltzmann distribution. So Boltzmann distribution tells us that the number of molecules Nj in a state with energy Ej at the temperature T. So this is proportional to exponential minus Ej over kBt. So here kB is Boltzmann constant. So I guess you already learned how to quantify the portion or the fraction of molecule in the specific energy level. So maybe in physical chemistry lecture. So the fraction of the molecule Fj in that state, so J is the index for the state. So that means, so we are going to sum all the number of molecules in a specific state. So and you want the portion of some specific state, so Ej over. So all we have to do is we can just replace the energy expression with our energy for the harmonic oscillator, and you can take the infinite sum for the denominator, and you can just put the single value for the nominator. So we discussed that in chemical thermodynamics lecture. So if you are interested in the statistics in the chemistry region, so you can take that course too. I guess that is the 4-semester course, and I also teach that class. So if you are interested in that, let's meet next semester too. And anyway, so when you plug in this expression, the nominator and denominator, and you can calculate the portion of the molecule in the specific states, and you will realize that, so let's assume the very common condition, so like temperature, room temperature 300 Kelvin, and the vibrational frequency like 1000 wave number, or you may want to try 2000, both of them, okay? So if you calculate the portion in the ground state, vibrationally ground state, and this is nearly 1. exactly it's like 9997 something. So that means in the vibrational spectrum, nearly all the molecules staying at the ground state. So all the molecules occupy the vibrational ground state here. So when you shine the light, then you will observe only the transition from the ground state. Okay. And the one last thing I want to discuss is the dissociation energy. So let's draw the potential energy surface of diatomic molecule, and it should be like this. So when the two atoms are too far from each other, they don't have any interaction and there is no orbital overlap between them. So their energies converges to the sum of two atoms' energy. So we take that as the zero. And at the equilibrium geometry, they would have the lowest energy. And when they get too close, and their energy diverges because of the strong repulsion between the positive charge in the atom's nucleus. And anyway, so this is the electronic energy. So if you want to say how much energy do we need to break this molecule into two atoms, so we can just say that this should be corresponding to the negative of minimum energy, right? This is the minimum energy. So if you apply, or if you provide the energy to the molecule that can overcome this potential war, then this molecule would be dissociated into two atoms, right? So this energy called the dissociation energy, dE, because we are only thinking about the electronic energy of that potential energy surface. But you might remember that the molecule does not really have the zero energy under the harmonic approximation. That means the molecule actually should be placed somewhere here. So energy difference between these two corresponds to the 0 point energy. 0 point energy. Because this is the diatomic molecule, so there should be vibration motion, and that means these molecules cannot have the zero energy even though at the potential energy minimum. So there is always 0 point energy. So if you actually measure the dissociation energy of this molecule, you will observe D0 rather than DE. So DE is considering only the electronic part of the molecule. So there is no consideration of molecular motion. So we can say that dE is the electronic energy required to dissociate the molecule into the atoms. But actually, due to the vibrational motion, we have to consider and we have to add the half of the HANU, which is the 0 point energy of that molecule. And this is the experimentally measured value. So their relation is D0 is dE minus half over HANU. Okay. Okay, let's move on to the next section. Okay, section 5.8. So harmonic oscillator wave functions involve Hermite polynomials. So we have established the quantized energy levels of the harmonic oscillator, and now let's look at the corresponding wave function psi v. Still we are discussing only the one-dimensional harmonic oscillator, so we have only the variable x. So this psi Vx, this describes the probability amplitude of finding the vibrating particle at a given position. Okay, we have only 5%. And the general solution to the Schrödinger equation for this system has a very specific form. So there is normalization constant and multiplied by Hermite polynomial. So even though this equation looks quite complicated, but actually not. So this NB, this is the normalization constant. So it is not quite new. So all the wave function contains the normalization constant because the square of the wave function is interpreted as the probability. So there should be always the normalization constant. And the second part, this is the Hermite polynomial. And this alpha is simply the some combination of constant. Mass multiplied by the angular velocity divided by h bar. And the final, this part is exponential part or Gaussian part because the exponential minus x square. So this part is required. The wave function decays to 0 at a large distance. So we haven't discussed the exact structure of a Hermite polynomial, but this is just the nth order polynomial. So that means they are not going to decay. They are not going to decay at the large distance. But for the well-behaved wave function, their value at the large distance should decay, and that's why we have this exponential function here. Okay, and let's try to derive that expression. And in the end, you will realize that the quantized energy level is also the result of this wave functions.